I'm going to speak about rounding errors, and especially I'm going to speak about how to find the bounds, like how bad can we round down or up. So yes. So oh yeah, first of all, my name is Yanis. I'm a security engineer at ChainSecurity. I audited a few projects. But anyway, today we're going to discuss. So first, to discuss rounding errors, we're first going to discuss some common patterns, like what's happening, what's going to be the limit, where is it going. Then we're going to discuss the vault share pattern that we can see in 4626 vaults, and then I'm going to show how to prove that we cannot be more far off than expected. And to do this, we're going to use Z3, which we're also going to see what this is. So first, why do we actually care about rounding errors? Well, for me, I care because it happens on all EVM chains. And where on EVM chains we can mostly only see integer math natively. And this always means that we are rounding down. Well, this also is often quite hard to guess. You can see some formulas, you see some math, as you saw previously, but it's hard to say like, oh, we're going to round down, but then we multiply, then we do something else, then stuff happens, and we actually don't know how far we're going to be. Because when we think, we always think this is going to happen in real values. So when we imagine like 3/2, we can easily imagine 1.5, or we can imagine some stuff, but it's not what's actually going to happen. So if later you multiply, then you're actually really far off. So we're going to see how we can a bit understand things that happen on chain. And also, usually this kind of issue, they wouldn't be flagged by any tools, or even I think AI is quite bad at finding this type of issues. So it's good if we can reason a bit about those. And oh yeah, and last reason, it happens quite often that there is a lot of money which is leaked by these tiny rounding errors. So yeah. So what we're going to see is like this kind of patterns, so simple, at the beginning somewhat simple expressions, and the goal is going to be trying to figure out how far can we be from the real value. So we're going to like see this value in solidity, where when we divide, like for example, if we do like A is 10 and then we divide by 3, well, we should get 3.333 something, but instead we get just 3 and then we multiply. So then we're again like way further away, depending on how big C is. So this is what we're going to try to assess, the difference between those two. And the first one we're going to be looking at is the most basic one we are going to see today, and we're going to ramp up the complexity. So if we have A A divided by B, then you probably all know that the further we can be away is almost 1. Like the worst case we can have is we were trying to reach maybe 3.99999 something. Well, we'll get only 3. So the further we can be away is 3, which is sometimes quite bad, sometimes quite good. But this we can easily reasonate about. We know it's going to truncate just the fractional part of the number. Now when we have like the expression we saw before, this one, maybe you also know how it works. In Solidity, if you just write this code, of course it's going to be first A divided by B, and then the times C comes later. So as we said before, the A divided by B, we can be, at most we can have an error of 1. So then we multiply by C, and this error also gets multiplicated, so we can be at most C away from the real value, the value that we have in mind that we expect. So for example, if we were supposed to get 3.99999 something, then imagine C is 4. Well, we expect to get like something like 12, but instead we will get just 9. So then we get a bit further away. So basically, anytime you see like a division, be careful, because you might want to actually maybe do the multiplication before instead, and like reorder the operations to get more precision. But you also have to be careful about overflows and stuff. So there is things. Now imagine we have this and we have D. We could like try to guess if it does anything. it actually doesn't. So like if we add stuff and everything, we don't actually change. It's not going to amplify the rounding error. It's just going to shift it a bit, but it's really multiplication and division we should be careful about in these rounding errors. So now, one which is a bit more complex, and on this one I'm going to spend a bit more time because people usually guess actually the wrong answer for this one. It's maybe not an expression we see every day. We're going to see some expression that we see a bit more later. But so basically, in this one, we have A over B. And then we have something a bit similar to before, where we had A over B times C. But now instead of the times C, we have times C over D. And in this case, we have C is smaller than D. So we cannot really amplify the error as before, because before we had C, which could be big, and then we really amplify the error. In this one, C over D is simply smaller than 1. So you could guess it's not going to amplify the error at all. And also, there is no issue with the parentheses. We're going to do A divided by B, then we do all this times C, and then we divide everything by D. Otherwise, C times D C divided by D would already be 0, and then this is all 0. Right, so there is no brackets error. Interestingly, so then most people say this should actually round down, but we're going to be at most 1 off because we cannot amplify. We have an error of 1, and then we multiply by something smaller than 1. So we just don't amplify the error. Well, actually, it turns out we can actually be two ways off, and this we can see in this example. So in this example, we have A, which is 5, and we divide by 3, and we get 1. Then we multiply by C, which is 2, and we get 2. And then we divide by D, with it, which is 3, and we get 0. So this is actually a bit more further away than... It's more than 1 off from what we expected. It's actually 1.11111, right? So we can actually be really further away than what we expect. Yeah, so this is the kind of things we should worry about when we check the math in a smart contract, because it goes a bit against our intuitions sometimes. And this is also why later I will show how we can prove this kind of a formula. Next, we have the case where C is greater than D. So in that case, we a bit come back closer to what we had with just times C, because now C is greater than D, so we can again amplify the error. So it's good to think about where we are in the, if we can figure out how big the numbers are going to be relative to each other, it can help us actually figure out how far the entire formula is going to be from the real valued formula. Yes, and then it turns out that the maximum error that you can get is sealing the C over D plus 1, which you can somewhat maybe, it's a bit similar to what we had before, right, times C, so this is the ceiling of C over D, and then the plus 1 also comes from the fact that we could have 2 ways of error in the previous formula. Yes, so now what I want to talk about quickly is, because for now we've been talking only about absolute error, so we're 1 way off, 2 ways off, C ways off, so we can be a certain number of units off, but what's actually interesting also is how far we can be in terms of percentage. So for example, if we have a correct result, the real value is 8, but we have a computed result of 6, then the absolute error is 2, right? The difference between the two. But if we have if we speak in terms of relative error, we have maybe 8 and 6, and then the difference is we're off by 25% compared to where we should be. So sometimes we do actually care about 1 way. We cannot be 1 way off, or we want to do something if we're 1 way off. And sometimes we don't care if we are less than 1% off. Maybe 1% off is fine. Maybe not. And now I want to talk about this formula that we often see. And this is the formula which comes from the 4626 vault from OpenZeppelin. So we have this formula to convert from share to asset. And basically it boils down back to this formula. And this formula, we're actually going to compare this time Because if we were to compare it to the real valued formula, right, we're back to the position A times B divided by C, and this is not really interesting. So we're actually going to compare this formula with the +1 to the A times B divided by C without the +1. So what does rounding do for us when we don't have the +1? So the goal is going to be to compare the real value target of A times B divided by C compared to the OpenZeppelin formula with integer. So what we would have on-chain against what we would have if we just think of a 4626 vault. We usually have in mind this simple formula of A times B divided by C. We have a share of the vault. That's what we own, and that's it. But that's not actually what's happening on-chain. And it's actually quite important to understand this kind of formula and how far can we be off from what we expect. And so the first question I want to ask is like, what is the maximum possible value of the difference, so the absolute error compared to those two formula? And of course, it's going to be quite big in absolute. Like if you have 256 bits of integer, the difference can be quite big. So I'm going to present like a small difference. This is actually the biggest that you can get with A, B, and C being smaller than 1,000. So it's like we have numbers smaller than 1,000, and we already have an absolute error of 512. So for example, if you take A being 512, B 3, C 1, this might not be numbers that you see every day in a vault, but this is what you can have. Then the real value is going to be 1,536, and the OpenZeppelin formula gives us 1,024. So that's a difference of 512. So if you just think, I have a vault, I have A times B divided by C, you might be far off. So it's actually quite important. And if you think about relative error bounds, it's even worse, because you can actually be 100% off if you take small numbers, of course, because if you have A being 1, B being 1, and C being 4, the real value is 1/4, right? We just have 1 times 1 divided by 4, it's 1/4. The OpenZeppelin formula is going to give you 0, because you do 1 times 4, and then you divide 1 times 1, and then you divide it by 4, then you get 0, it's going to round down, right? So you can be 100% off for small number, and you can be really far for big numbers. Another question is, those two, we actually round down, right? Because we divide, so we round down. This is what you initially think. And the question is, are we correct? Like the real value was 1,500, and we go to just 1,000. This one was supposed to be 1/4. We go to 0, so we round down. But is it always the case? Can we go higher? We have a division where we round down, but we do have some +1s. So can we go higher than the real value? And the answer is actually yes, you can go higher. So this is a bit unexpected when you think about we just round down. But no, actually we have +1s. So if, for example, you take A being, the numbers are a bit less nice. So, but yeah, you can verify the math, right? If you take A being 189, B 1, C 20, the real value you should get is 9.45, and the OpenZeppelin version gives you 18. So this is actually nearly twice as high. It's really far from what you would expect. Now, what I want to show is quickly how we can prove those simple formula, like prove that we cannot reach a difference of 3, or we cannot reach a difference of D. We cannot be that far from the real value. And to do this, we are going to use Z3, which is an SMT solver. So this is basically a tool which allows us either to find a counter example if there is one, or to say there is no counter example which exists. So we will say SAT for satisfiable or unsat. Yes, this is basically like fuzzing, where you would try to find a counter example, but in this case, we know if we cannot find one, we know that there is no counter example, so we know this cannot be satisfied. So what it's going to look like is like a small piece of code like this. Actually, this is all the code you need to prove A divided by B times C, and to prove that we cannot be further away than C from the real value. And I'm going to walk you through the code quickly. And basically the way it works, like you just import Z3, right? Then you have A, B, C, you define your integers, the ones we have, and you can make some bounds. So In my case, I just want them to be bigger than 1. That's enough. And then I just put the two the two formulas I want to compare. So the computed one on chain, where I don't do anything, it's going to do integer math by default. And the real one, where I convert from like 2 real values to get the actual real value result. And then I can compute the error and the absolute error. And then I can add a new condition. So basically what I do is I have this solver, which is the solver from these 3, and we're going to solve for all these inequalities or conditions. So now we have like 2 conditions, or 4 conditions, right? We have those 4, and we also want the absolute error to be greater or equal than C, where the absolute error is defined like this. So you just can put some Python math, you put your variables, a bit of Python math, what you want to look at, and that's it. Then it's going to tell you, you call the function check, and it's going to tell you, is it satisfiable? Like, can we have A, B, and C, which are going to satisfy all those conditions, or can we simply not? And if it says you cannot, then it means that there is not a single A, B, and C which are going to satisfy this. So in our case, this is asking, can the absolute error be greater or equal than C? And if you run the program, it's going to say, unsat. This means that there is not a single A, B, and C which are going to give you an absolute error bigger than C. So you can be sure, and this is for a simple formula, right? But you can imagine that if you have a bit more complex math, or if you have operations in a different order, it makes it really easy to say, which number you cannot reach, and if this is fine for you. And now, like, to be sure it works, like, because you don't see a counter example, you don't see anything, you just see unsat, like, can you really believe it? Maybe I made a mistake in the Python script, maybe there is something wrong. Well, maybe your intuition is like, you can be maybe like at 0.999 of C. So you just do the same thing, but you replace C by 0.999 of C. And now, instead of saying unsat, it's actually going to say sat, and it's going to give you a counter example. So you can be at 0.999 of C with this ABC. So makes it quite easy to check your formulas. Let's look really quickly at a more complex one. But basically, this is the OZ formula we just saw before. And the goal is to prove we cannot be, because I said we can be higher than this formula compared to, we can be higher than 8 times B divided by C. And so we have the same setup, right? We have the same computed wheel where I put this. And now I want to show that we cannot be 100% off. So we cannot be twice the real value. This is going to show, again, unsat. We cannot find A, B, A, and C such that we are twice as high as what we should be. But we can find A, B, and C such that we are times 1.99999 the real value. So we can be nearly as twice. So twice is like the bound, how far we can be off in terms of rounding errors. Yes, and this is actually all I wanted to say today.
Thank you, Yanis. Do we have one question for Yanis? Yeah.
My guess is that if you have a very complex problem with a lot of operations, probably solving this is MP hard. So I assume that you cannot have really big programs. So could you share how far you can go with this solver? Do you have some experience?
No, this is actually quite a hard question. How far can we solve, right? It depends on the power that you have. It